This is a sample test question involving usage of the I2c bus. The microchip 24LC515 is a serial Eeprom that's used in lab. Give a snippet of C code that reads the byte at address 1234 in the Eeprom, adds 1 to it, and then writes it back to the same address. We're going to assume that all writes have completed before we do this operation. Pins A1 and A0 on the Eeprom are both tied to ground. So step 1 is to read the byte from the I2c Eeprom. To do this, we need to do what's called a random read from the Eeprom. This consists of actually two separate I2c transactions. The first I2 transaction is a write transaction in which we're going to write the address to the Eeprom. So let's first do that. It's going to start out with a start condition, so let's do a start condition. So we'll do a start I2c1. At that point, then comes the very first byte, which is going to be the address byte of the I2c device. The format in this case is going to be this 1010 followed by the block bit, which we'll talk about in a second, followed by the values of the A1, A0 address lines on the Eeprom, followed by a 0, since this bit right here is the read-write bit, and this is a write transaction, which means it's going to be 0. So let's do that in binary, 1010. The block bit is only a 1 if this address that we're trying to access is 8,000 or greater. Since this is less than 8,000, this block bit's going to be a 0. We've tied pins A1 and A0 on the Eeprom to ground, so both of these bits are a 0. Since this is a write transaction, this bit's going to be a 0, so the final hex value of this is going to be an A0. At that point, we need to send the address high byte, and then we need to send the address low byte. So let's do that using a put I2c. The address high byte is 12, so we'll send that. We'll do a 34, which is the address low byte. At that point, we need to do what is called a repeated start. This is like a stop followed by a start, except we'll just do it with one call. So we're going to do an R start to start the next transaction. This next transaction, which is going to be here, is going to be a read transaction. So we first need to start it, so let's do that. We've already done that with the R start. We then need to send the byte, the address byte of the I2c device itself, which is going to be the exact same form as before, except since it's a read transaction, this last bit here is going to be a 1. So this byte that we stand is going to be the same as before, 0, 0, 0, except this last bit, it's a read transaction, is going to be a 1, so it's going to be an A1. At this point, we now need to read the byte that's coming back from the Eeprom. So in order to do that, we're going to do a get I2c. This parameter here is going to be the ACK bit that's going to be sent by the PIC24. Since this is a read and we're reading, this is the last byte we want to read from this device, this ACK bit is actually going to be a NAC. It's going to be a 1. We can see that in this diagram right here. This is a NAC here, so that's a 1. So we're going to send the 1 there. We're going to, the byte that we get back, we're going to store in a temporary variable, and then we need to end the transaction by doing a stop I2c. We can see that right here by this stop. At that point, we've done this complete random read of the Eeprom. We've read a byte from location 1234 and stored it in this temporary variable U8X. Now that we've read the byte from the Eeprom, we need to increment it and write it back to the Eeprom. So in order to do that, we need to implement this byte write transaction, which is going to be an I2c write transaction. We're going to need to do a start, so let's do that. So we'll do a start I2c. At that point, we need to send a control byte, same format as this for a write transaction. So we've already gone through those details. It's going to be a 1010 0000, so it's going to be an A0 here in hex. We then need to send the address high byte, the address low byte, so let's do that. Address high byte, address low byte. At that point, we need to send the byte that we're trying to write. So here's the data that we're trying to write. We're going to take the byte that we read, we're going to increment it by 1 and send that, which we've just done. And then we need to end the I2c transaction with the stop. So we'll do that, stop I2c. At that point, we have solved this problem. This problem is the same as the previous problem, except I took this address, the previous address was 0x1 2, 3, 4, and I set the most significant bit of this address to a 1. So this hex 0001, that becomes a 1, so this digit becomes a 9. The most significant bit of this address is now a 1, which means that this address is greater than or equal to hex 8000, which means that it is in the upper 32 kbytes of memory. How does this problem change when I make this one simple change? Well, what happens is that now what I need to do is that this byte right here, which is the byte that contains the I2C device address, this block bit must now be a 1, because this block bit is actually the value of the most significant bit of this address. So anywhere I send this byte, where previously it was a 0, it's now going to be a 1. You can see how these values changed. You would think that another change I should have to make is that when I send this address here and I send the most significant byte, that this should have to change to a 9-2 to match this. However, if you take a look at this transaction and you take a look at the high address byte that's being sent here, this X here means that the most significant bit of this high address byte is actually a don't care. It's ignored. Why is it ignored? It's ignored because it's actually the block bit that actually contains the most significant bit of the address. So in this case here, when this address was greater than or equal to 8000, that means this block bit here is going to have to become a 1 in order for this to operate correctly. We want to point out that treating the I2C device address like this, where we're using this particular bit to mean something in terms of the function of the device and not actually being an external pin, typically that's an external pin on the device, is not standard for the I2C protocol. This is simply how this particular I2C device works. Typically, these 3 bits right here would actually be reserved for physical connections you would actually make for the device, but Microchip made the decision to use these 2 bits for physical connections on the device to change the device physical address, and then use this bit here in the I2C address to mean something in terms of the internal functionality of the device, and this is not standard use of the I2C protocol. This is very specific to this particular device. One of the beauties of the I2C interface is that its generic format allows you to interface new devices fairly easily just by reading their datasheet particulars. For example, here's a datasheet for a TMP 100 temperature sensor. If we wanted to use this device, the first question we want to know is, what would be the unique I2C address that we could use for this device? So let's assume, this is the pin on the device. It's only a 6-pin device. SCA on SDA 2 is the clock and data lines for the I2C device. Ground and power, supply ground and power to the device. These 2 pins right here personalize the I2C address of this device. Let's assume that these 2 pins are tied low. Then looking in the data sheet, we find this table right here that gives us the slave addresses for the this device, assuming different values for these 2 external pins, add 1 and add 0. If we assume that these are tied to 0, then we have both of these lines as 0, and the 7-bit slave address would be 1001000. Now at this point we would ask, what is the 8-bit I2C address required to write to this chip for this configuration? Well, the 7-bit address, the 8-bit address is going to be, the upper 7 bits will be this slave address followed by the read-write bit. We know that if we're doing a write transaction, an I2C write transaction, then the value of this read-write bit would be a 0. So if we group these in 4 bits to get a byte, we find that this byte that we would write out as the very first byte in an I2C transaction would be a 9-0. Now that we know how to write to this chip, what about if we wanted to read from it? So let's keep our assumption the same, that these pins are tied to ground. That means our 7-bit address is going to remain unchanged. And if we're going to read from this chip, then our 8-bit I2C address, the only thing that's going to change is this read-write bit, was going to change from a 0 to a 1. And now this byte, if we group up 4 bits, this byte is now going to change to a hex 91 for an I2C read transaction. So once you know how to talk to a particular device via its I2C address, in this case I2C address for these assumptions would be a hex 91 and I2C write address would be a hex 90. Once you know that, the next question is how to get data in and out to particular registers inside of the device. Typically the device will have different registers that contain values that we want. In this particular case, since this is a temperature sensor, there's a temperature register inside of it that will contain the temperature that we want to read to see what temperature it's measured. So how do we actually get access to that temperature register? In reading the data sheet, it turns out that there's this other register called the pointer register that has 2 bits that can be non-zero, and that in order to access one of these other registers, temperature register, configuration register, T-low register, or T-high register, you first have to write a value to the pointer register to point it at a particular register. And so the way that this works is that if we write a value of 00 to these 2 bits in the pointer register, then the pointer register is now pointing at the temperature register, and if we read the device, we will be reading the temperature register. If we wrote the value 01 to these 2 bits, so we wrote a value 01 into this pointer register, then it would now be pointing to the configuration register, and if we now read the device via an I2C read, we would actually be reading the configuration register. So this question is, how is accessing a particular register in a temp 100 accomplished? It's accomplished through this pointer register, and the location of the temperature register is going to be via the pointer register by writing a 00 to this pointer register. So the next obvious question is, now that we know how to read and write internal registers, how do we read a temperature out of the device? Well, the temperature is a 12-bit value. It's going to come back in 2 bytes. The first thing to do, we're going to do a write transaction to set the pointer register. So this is going to be a write transaction. The read-write bit is going to be a 0. I'm going to set these 2 P0, P1 bits to a 0 to set the pointer register to point to the temperature register. Then we're going to do an I2C read transaction here. Here the read byte's a 1. The first byte that comes back is going to be the upper byte of the temperature. The second byte that comes back is going to be the low byte of the temperature. So it's going to be 2 I2C transactions, a write transaction to set the pointer register, and then a read transaction to read 2 bytes back, which is going to be coming back from the temperature register. So let's write some code for reading the temperature register. Recall that it's going to be 2 transactions. First, a write transaction that's going to set the pointer register value. That's going to be this transaction right here. So first we need a start. So we do a start I2C. We now need to write the I2C write address of a 90. That's going to be this guy right here. These 4 bits are a 9. This is a 0, 0, 0, 0, which means the last hex digit here is a 90, so this byte is going to be a 90. Now we need to write the pointer register value, which is going to be the next byte that goes out. So this is the pointer register byte. These 2 bits being 0 points the pointer register at the temperature register. So we're going to write a 0, and now we need to stop the transaction to complete the write transaction. So that's going to be the stop condition here. And at that point, we have set the pointer register to point towards the temperature register. At this point, we now need to do a read transaction to read the temperature register. That's going to be this transaction right here. So we're going to do a start first. So we do a start I2C. We need to send the I2C read address of a 91, which is exactly the same thing as the write address value, except the least significant bit is a 1. So if we look at this, this is a 9 here. This is 0, 0, 0, 1. So the only difference here is that this is a 1, that's a 0. It's going to be a 9, 1 that we send out. At that point, we now, since this is a read transaction, the device is now ready to send this data. So we're going to do a get I2C and read the high byte of the address. Since we're going to read another byte after this, this value here that we're sending to it needs to be a 0, which means it's an ACK. It means that we're not finished reading data from it. So this is the ACK bit that's getting sent back by the PIC, which is this guy right there. It's a 0. We'll store that byte that we get back in a temporary variable. We then do another byte read here, get I2C, read another byte, and this time, because this is the last byte that we want to send, we're going to send a NAC, a 1 value. That's going to say don't send us any more data. And then we're going to do a stop I2C and end this write transaction. And at this point, the 2 bytes of our temperature are sitting in these 2 8-bit variables. Let's take a look at another I2C device, the INA209. This happens to be a current power monitor for measuring current and power. It has an I2C interface. Let's assume that its I2C device address has been personalized to be this, a 10000011. This is the 7-bit address followed by the read-write bit. That means that an I2C read address transaction would be this byte right here, an 87, while a write address transaction would be an 86. The only difference would be the least significant bit, a 1 for a read and a 0 for a write. It turns out that this particular device also uses a pointer register to access internal registers, and this table right here shows a partial listing of the registers inside the device. This device has many registers inside of it. They're all 16 bits wide, and let's say that we're interested in this register right here, the bus voltage register. This will return the bus voltage that it's measuring. Let's write some code to read the bus voltage. First thing we got to do is we got to set the pointer register just like we did with the previous device. So we do a start I2C. This is a write transaction, so we'll send an 86. That's our I2C write address. We now need to set the pointer register. For the bus voltage register, the pointer register value is a 4. So we're going to set a 4. We then do a stop. We've now completed this write transaction. So now we need to do a read transaction. So we'll do the start. Then we're going to send the byte, the I2C device address for a read, which is going to be an 87. Now the device is in read mode, so now we can get the 2 bytes. The first byte that's going to come back is going to be the high byte of the bus voltage. We'll store that in a temporary variable. We'll send an ACK because we need to read another byte. We're then going to do a get I2C send it a NAC and store that byte that comes back is going to be the low byte. We're sending it a NAC because this is the last byte that we want to read, and then we're going to stop. What I want you to notice here is that even though this is a completely different device, this is a power monitor device. This code back here was a temperature device. The code for these 2 devices, this is the code for the temperature device, this is the code for the power monitor device. It looks almost exactly the same because I2C devices in general work very similar to each other, and that's one of the advantages of the I2C interface. Once you learn how to write I2C transactions and read data sheets describing I2C transactions, it becomes very easy to write I2C code to talk to an I2C device. Do not get too used to the idea of a pointer register in I2C devices. Not all I2C devices use pointer registers. Some devices will simply give you a particular transaction sequence of bytes in the transaction needed to access a particular register. For example, the TMC222 is a stepper motor controller. This particular extraction from the datasheet shows how to set the position of the stepper motor. We set the position of the stepper motor by first sending it the I2C device address. The I2C device address, the first 7 bits are the address of the device itself. The last bit is the read-write bit. This is going to be a write transaction. The 2 bits, the 2 upper bits of the 7-bit device address are both 1s. These next 4 bits here are one-time programmable only bits. That's what OTP stands for. You can program to set this device to have a unique address. Let's assume that these bits are all programmed to a 0. This next bit right here corresponds to a bit on the device that can either be set high or tied either high or low. Let's assume that this is tied high, so that this bit right here is a 1. Then these next 3 bits here, these next 3 bytes here, specify the set position command. We then specify the position of the stepper motor via a 16-bit value. We send the upper byte first, followed by the low byte. So let's write some code to implement the I2 transaction in this table. So we've assumed that the I2C device address is this. We assume that all of these bits here were programmed to 0, so that's these 4 bits here. We assume that on this particular device, this pin is tied high, making this value, this bit here, a 1. So the write address for this transaction is going to be a 11. 0000. This pin right there is the HW bit. It's tied to a 1. And finally, this is the read-write bit right here, which is a 0. So this is going to be a C2. That's going to be this very first byte in the write transaction. So to write the code for the step promoter position, we'll do the following. We'll do a start I2C. We'll start the transaction. We'll send this C2. We're then going to send these next 3 bytes here. This byte right here, that 4 bits is an 8. This guy right here is a B, so this byte right here is an 8B, so we'll send the 8B. These next 2 bytes, if we see, these are all 1, so this is an FF. This next byte here is an FF as well, so we'll send the FF, we'll send the FF. At this point, we need to send the 16-bit step promoter position value. Let's assume that this 16-bit step promoter position value is contained in this 16-bit unsigned variable SPOS. To get access to the upper byte, what we're going to do is we're going to take this guy and we're going to shift it to the right by 8 bits. That's going to move the upper byte into the lower byte. We AND that with an FF. We typecast that to an 8-bit data type, and now this byte is going to be the upper byte of this 16-bit value. We'll send that. At that point, we now need to send the lower byte. So we'll take the 16-bit value, AND it with an FF, typecast it to an 8. That's going to get access to the lower byte. So now we have the lower byte. We'll send that via a put I2c, and then we'll do a stop I2c, and the transaction is finished. So these last 2 bytes we sent was these 2 bytes of the 16-bit step promoter position. The previous code used shift operations to actually get to this upper byte here. Another way to do it is simply take this 16-bit value, divide by 256. That's the same thing as shifting to the right by 8. That will be the most significant byte of the 16-bit value. To get to the least significant byte, what you can do is you can do the mod operator here, which says it's the remainder. Whenever you divide by 256, that will return a low byte. So you simply can use whichever versions of this code that you wish in order to get access to the most significant byte and least significant byte of this 16-bit value.